All right, if you're ready to get started, say, oh yeah. Oh yeah. It sounds like a Monday morning. If you're ready to get started, say, oh yeah. Oh yeah. Excellent. All right. Welcome. Today we will be presenting on mastering Android security research, and we'll be presenting a guide for the modern security researcher. You're probably wondering, who are these people? Why should I listen to them? I'm Hahna Latonick. I currently serve as the Director of Security Research for Dark Wolf Solutions. I've been working in the defense industry for the past 18 years. I've also served as a cybersecurity subject matter expert on Fox Business News, ABC, and other national media outlets. I love participating in CTFs. Two of my proudest moments is last year our team tied in first place for the 2023 DEF CON IoT CTF. And in 2014, my team and I competed in the main stage CTF event at DEF CON, placing in 6th and ranking the top 1.5% of ethical hackers worldwide. I also hold several cybersecurity certifications, including my CSSP, Certified Ethical Hacker, and I'm also a certified Android exploit developer. Lastly, I have 2 pieces of paper, a bachelor's and master's in computer engineering, along with a mathematics minor, and I'm joined with my co-presenter, Jacob.
Good morning, everybody. My name is Jacob Swinsinski. I'm currently a security researcher over at Dark Wolf Solutions, working directly with Hahna. So my expertise is in quite a couple different areas, specifically in reverse engineering, binary exploitation, vulnerability research, now more specifically Android security, and my background is heavily focused on pen testing. So I hold 5 different certifications, including the Practical Network Penetration Tester, the eLearn Junior Penetration Tester, as well as the Security Plus, and then I also have a Hack the Box Pro Labs certification, also known as Dante Pro Labs. My background in schooling is I have a bachelor's in information systems with a focus in cybersecurity, and I obtained that from Pittsburgh Technical College.
Excellent. Now, we're going to cover a lot in this 45-minute talk. First, we're going to provide an introduction to Android. If you're completely new to the topic, raise your hand. Excellent. And if you've been conducting Android security research or maybe doing Android pen testing, we want to set the stage so that we're all on the same page. Then we're going to dive into our Android security research methodology and how to set up the proper lab to conduct this type of research. Then we'll go into each stage of the process, first starting with reconnaissance of researching your target, then performing static and dynamic analysis in order to discover vulnerabilities and how you can do that at scale using a technique called fuzzing. Once you have identified vulnerabilities, in order to demonstrate their severity, first you need to bypass exploit mitigations and security protections. So we'll talk about the different types that you'll need to consider, as well as different types of cyber effects that you can demonstrate through exploiting those vulnerabilities. So without further ado, let's dive into an introduction to Android, which will be presented by Jacob.
Thank you. So let's get into the introduction to Android. So Android security greatly plays a major role within the world of cybersecurity in which we know today. I'd like to direct your attention to the 2 illustrations pictured in the middle of the screen. So specifically, we have 71% of the total mobile operating system market share is made up of the Android platform, which is just absolutely staggering. Next, we have 3 billion Android devices actually populating the Earth, which is unbelievable as well. So given those staggering numbers, as well as the diversity and the fragmentation of the Android ecosystem, being able to wrap your head around these types of vulnerabilities within the Android operating system has become more important than ever. So with that said, let's get into the architecture of Android. Android is an open sourced operating system that's based on the Linux-based operating system and comes in a wide array of different types of form factors and different devices. Its documentation has been made conveniently open sourced and available through the AOSP, or Android Open Source Project. And I'd like to direct your attention to the Android software stack, specifically with the Linux kernel. So with the Linux kernel, this serves as a subsidiary and intermediary type of program that sits in between the operating system as well as the bare metal hardware. And essentially, the Linux kernel allows us to gain access to those bare metal hardware pieces. Next, we have the native C and C++ libraries. This allows us to implement native functionality and native implementations such as the libc library within our applications. And lastly, the Java API framework. This allows us to actually go in and manipulate our Android application as well as the ecosystem. So really cool stuff there. Next, we're going to get into Android applications. So currently, Android applications are written in 3 different languages, those being Java, C++, and Kotlin. So Android also conveniently offers a SDK or a software development kit in order to be able to easily implement all of your program's logic as well as any of the features and other audio files as well as imagery within your program. And that's all bundled into 2 different files known as the Android Package Kit or APK. And you can actually bundle all of those together, including your resources, and that's known as the Android App Bundle. It's important to know that after Android 9 Plus and up, each and every single Android application actually operates within its own sandbox virtualized environment. So that means that it only has access to the resources and the functionality that it needs. Next, we're going to be getting into Android application components. So what actually makes up these Android applications? So this is split up into 4 main parts. First, we have activities, which represent the GUI-based interactions and the overall representation of basic functionality within the application and handles user interactions. Next, we have services. Services actually perform background tasks and are utilized even whenever the program is not in use. Next, we have broadcasts. This serves as a receiving and sending functionality for a series of broadcast messages that can be relayed throughout the application that listen and respond to various different requests and broadcast messages, as well as system-wide events. Lastly, we have content providers, which simply just manage and share data across a native application or third-party applications. Next, we have Android intents. So previously, we talked about Android components. Well, how do we actually use those Android components? So we can use intents to actually call upon these Android components, and as a result, that's how we invoke those actual components. So, intents serve as a communication mechanism and a sort of layer in between being able to call out components and actually being able to specifically utilize them in specific use cases. So more specifically, for activities and services, the intent just simply defines the action to perform. Now for broadcast receivers, the intent defines the actual broadcast message/announcement in general. Next, we have the APK or the Android Package Kit. So I'd like to make it known that every single APK in the whole entire world includes a file known as the Android manifest.xml file. This is arguably one of the most important files whenever it comes to Android applications, and as a result, if this file is not included in your binary, it will not compile. So definitely something to keep track of. So it's actually responsible for declaring everything that's necessary for the program's logic to be able to run properly. And it also includes various different resources, like I mentioned earlier, audio files and images, but it's important to note that that is stored separately from the actual APK itself, just in order to optimize overall usability and functionality within sharing application code, just to simplify the process.
Cool. Thanks, Jacob. So now that you have an understanding of, we'll say, Android foundations, let's talk about Android security specifically. Android strives to provide the most secure software to their users, and they do this in a variety of ways. First, they implement several security features, such as application sandboxing, providing secure inter-process communication mechanisms, as well as code signing or application signing to verify the integrity of the application that you're using. They also provide a security bulletin where they're very transparent about the security vulnerabilities and weaknesses that have been reported, along with additional remediation guidance. Android provides very comprehensive security documentation about their security model of how they protect the app's data, the user's data, as well as protecting the system resources on the device. In addition, we want to make you aware of the OWASP Mobile Top 10 risks, which provides details on existing and emerging threats to mobile application security. I highly recommend becoming very familiar with these different resources, documentations, and features, as it's going to greatly aid your Android security research. Now, you might be wondering, well, how do I get started in performing Android security research? As Jacob had mentioned earlier, the Android ecosystem is very fragmented with several different operating system versions and device manufacturers. In addition, Android security tools that were once popular have now become either obsolete or they're no longer maintained. Therefore, we created the Android Security Research Playbook as a getting started guide to showcase how security researchers can conduct their research successfully against modern Android targets. We have open sourced the ASRP on GitHub, and we've also developed a dedicated website. Don't worry, you'll get access to these slides. There's also a QR code at the end, and URL links if you don't trust QR codes. But one thing we want to clarify and make note of is that the ASRP isn't all inclusive of every single tool or approach or method that is currently available. However, it provides several recommendations for each stage of the process so that you can continue making progress with your research. So what is the ASRP methodology? It consists of 7 stages, as we mentioned earlier in the introduction. First, we'll describe reconnaissance of how to research your target, then how to conduct static and dynamic analysis and the tools that are necessary to conduct these stages successfully, the different types of classes of vulnerabilities that you can discover, as well as different types of fuzzing tools that are available for use, the different classes of exploit mitigations and security protections that you'll need to bypass, and then the different types of cyber effects that you can demonstrate through exploitation. But first and foremost, you need to make sure that you have the right environment set up to do your Android security research. We highly recommend using emulation software that allows you to create different types of emulated Android devices. So whether it's a Samsung S9 or a Google Pixel 3, for example. You can use Genymotion, which you can install on your laptop or desktop. They also provide cloud images as well that you can deploy on AWS or GCP. And with that, they do provide a personal license or a free trial, but also a professional subscription for access to additional features. There's also the Android Studio. This is the IDE that's typically used when developing Android applications, but it also comes with a free emulator. I love free, I'm sure you do too. However, it is a bit computationally intensive and a bit slow, but hey, it's free, right? You get what you pay for. And then there's Corellium. They have been a game changer in this field. They offer a SaaS platform where you can emulate both Android and iOS devices, and they provide a lot of advanced features for conducting your Android security research. In addition to creating emulated devices, we highly recommend using virtualization software. The last thing you want to do is examine a target on your host machine and corrupt your laptop, right? That sucks. Instead, use a virtualization software such as VMware Workstation Pro. They, again, offer a free 30-day trial as well as a paid subscription where you get access to advanced features such as snapshotting. But if you're on a budget or if you only like free, like me, you can use VirtualBox, which is also available. In addition, the ASRP provides additional hardware and software recommendations, so we highly recommend checking that out so that you can identify what's appropriate for your particular project. So without further ado, let's talk about the first stage of reconnaissance.
Thank you, Hahna. So we're going to be getting into reconnaissance. So this is split up into a category of 5 different plays. So the first one being gather open source resources. So why would the security researcher want to do that? Well, in this play, we are tasking the security researcher to go out and perform OSINT, or open source intelligence, on the particular target that we're pursuing, and just go out and gather documentation, any blog posts that are regarding any exploitation, as well as any documentation for that target. Next, we have contextualizing the history of the target. This is done for a couple different reasons. The main reason is to understand the overall motivation as to why the target exists in the first place. This helps boost the overall understanding as to why we're performing Android research on this particular target, as well as why it's so valuable and why it's a target in the first place. Next is discovering any known CVEs. This is arguably one of the most important plays within the reconnaissance. section. This is because oftentimes they're not. Whenever vulnerabilities are found within systems, developers quickly want to get that patch and that mitigation rolled out as quickly as possible. However, that still leaves them open to attack from other attack surfaces, and oftentimes or not, you can actually still end up exploiting the original vulnerability just by tweaking the original proof of concept. So definitely something to look out for if you hit a plateau and you need to make a pivot with it during your security research. Next, we have curating a list of capabilities. This is pretty simple. It allows us to understand exactly what the target is capable of, what exactly its purpose is, and what it can do. Lastly is finding sources for the APK. So we want to find sources for the APK so we can actually obtain the file itself that we want to obtain. We want to perform static and dynamic analysis on. There's a couple different ways that we can actually obtain the APK itself, and that's through a primary method known just utilizing the Google Play Store, and there's also third-party methods that utilize what's known as APK Pure. So with that said, I'm going to pass it over to Hahna to go into static analysis.
Excellent. All right, once we have collected our target, we're now ready to perform static analysis, where we're going to examine our target's code without actually executing it. And we're going to utilize a variety of tools to help facilitate this process. First, we want to understand the APK's design and compiler using APK ID. In this example, we can see that this particular APK is using anti-virtual machine checks. We'll go into this a bit more in the presentation, but essentially it's checking to see whether or not the APK is running in a virtual environment. We can see that it was compiled using DX or possibly DexMerge. We also notice that it's using anti-debugging checks as well, which can prevent us from conducting dynamic analysis, which we'll talk about shortly. And we also see that it uses some anti-disassembly mechanisms as well, which can help hinder the reverse engineering process. So even though we haven't really executed or dove into our Android application, we've already learned a lot about its design and its compiler. Next, we want to decompress and decode the APK using APK tool. In this example, we can see that it's extracting its resources, it's decoding the Android manifest file that Jacob talked about earlier. It's also extracting its assets and libraries. And in addition, it's also extracting its classes.dex file. This is actually the compiled bytecode that gets executed when you run your application. Next, we want to decompile the APK using JOTX. Who here has ever used the Ghidra decompiler? Right? So the Ghidra decompiler essentially converts the disassembly of a program and converts it into a high-level pseudo-C-like language. This is very similar, but instead of converting it, the compiled code to C or C++, it's decompiling it to Java. So rather than looking at the bytecode of the classes, we can actually recover its corresponding Java code, which is much more easier to interpret, to understand the functionality of the APK. We can also export this project as a Gradle project and import it into Android Studio in order to examine the file structure in a more, we'll say, robust IDE. And so here we can see that we have our Android manifest, our Java packages, its resources, as well as the Gradle scripts that were used to build the APK. Next, we want to analyze the APK's library files using the Mobile Security Framework, or MobSF. We can see in this example we have 17 activities as well as one provider for this APK. We can also analyze its permissions to see which are present or which are absent. We can also conduct additional malware analysis, reconnaissance, but what's great about MobSF is that we can specifically gain additional information about its shared libraries. We can take it a step further and do some more low-level analysis by reverse engineering the library files using Ghidra. In this example, we can see that the main activity has a function called leak memory, which is very interesting. And as we're analyzing this code, I can see that it's utilizing the function called snprintf, which is actually a known insecure function. So if I'm looking for vulnerabilities, I probably want to spend a bit more time reverse engineering this particular function within this APK's shared library. Next, we'll conduct dynamic analysis, where this time we're actually going to examine our target while its code is executing. And as you can see here, we have a variety of tools that we'll be utilizing. So first, what we want to do is connect to our emulated device using the Android debug bridge, also known as ADB. Next, we want to install the Frida server. This is going to enable us to perform dynamic instrumentation and gain greater introspection into our target. Once we've done that, we're now ready to install our target application. In this example, this is the DAM Insecure Vulnerable app, which is our target. Once we've installed our application, we can now examine its runtime behavior using objection. In this example, we're executing Android commands in order to hook into the main activity, where we're searching for what lists of methods does the main activity encompass, right? So we can see here that this application is checking for a PIN, right? Usually we have a PIN to access our phone or even our applications. We can see that it's possibly performing some arithmetic operations, as there's a sum function. So just this listing alone, we can gain a lot of information about our application. And then we can also perform real-time monitoring using the Runtime Mobile Security, or RMS. What I love about this tool is that I can actually interact with the application and in real time see what classes and methods are invoked, right? Because I can take that information and then use that as a part of my reverse engineering process. We can even debug our applications at a very low level using the GNU debugger, or GDB, along with its GDB server, right? So for example, if I want to better understand the context of its register state, what data is on its stack, and more, I can perform that low-level analysis using GDB. And in this example, in deploying an exploit, I can see that I've overwritten the program counter, which means that I can control the code flow or execution of my application, so my exploit is working as intended. And then if I am analyzing an Android app that is, let's say it invokes a web page or it's communicating with a server, I can monitor and intercept that web traffic or even network traffic using Burp Suite proxy, right? So I can click on these different packets and sessions and see what data exactly was being transmitted from my source to my destination and vice versa. And so once you've conducted your static and dynamic analysis with the goal of finding vulnerabilities, there's different types of classes that you can find.
So after all of your hard work, from reconnaissance to static and dynamic analysis, it's time for the fun part. Let's start breaking some code. So getting into vulnerability discovery, the first vulnerability class that we have is a textbook standard buffer overflow. Simply put, this is whenever the data of the allocated size of the buffer actually exceeds that buffer size while it was instantiated. And then ultimately from that, that data begins to overflow past the buffer into other adjacent memory regions. This can lead to a multitude of different vulnerabilities, such as remote code execution, memory leaks, etc. Next, we actually have an integer overflow. This occurs whenever the operation of two arithmetic integers actually exceeds the data type that was instantiated for the variable type. You can see in the illustration, we actually have an odometer that is rolling over from 999,000 miles to 1 million, and where it should be 1 million, it rolled over to 0. So that's a perfect depiction of an integer overflow. Next, we have a write what where. A write what where condition is a condition that could potentially be the presence of the effect of a buffer overflow, and essentially it just allows an attacker to perform an arbitrary write to an arbitrarily attacker-controlled memory location. So in the C code snippet above, you can actually see that we have a defined global of buff size that is given 256 bytes, and then you can see that it takes a single argument for our binary. There is then a call to a vulnerable stir copy that actually copies the contents of our first argument into buffer 1. Lastly, there is a call to free our second buffer that was created. And if you actually inputted a string that was larger than 256 bytes, what will happen is upon that freeing that second buffer, the memory allocator will actually leverage a linked list, and as a result, that linked list will become corrupted due to the pre-existing buffer overflow, allowing the attacker to replace that linked list with a attacker-controlled memory region, as well as arbitrary data, leading to remote code execution as soon as that pointer gets dereferenced. Next, we have a use after free. This is any attempt to access memory after it has been freed. So this occurs constantly, or this can occur whenever you are performing dynamic memory allocation. So specifically, you want to pay attention to two main functions that utilize dynamic memory, such as malloc and free. So anytime that you actually see a free call, a malloc call, make sure that we're freeing the data after use, or if you see a free call and that data is being referenced once more, this could result in a use after free vulnerability. Next, we have a format string bug. This is personally one of my favorites. It actually occurs due to developer error because the developer, whenever he or she were creating the code itself, they did not specify a format string specifier as an argument for the actual function itself, such as printf or sprintf, for being able to print out data and strings. So as a result, the attacker can then supply their own format string specifiers, such as %n, and we can then write data to the stack dynamically and at will. Next, we have an information leak. This is just a generalized term for the unintended exposure to data, and it's also known as a memory leak. You can actually see in the illustration above, this is a famous, or infamous depiction of the Heartbleed vulnerability, and you can see that the user is requesting data from the server, and upon the server actually being exploited by the Heartbleed vulnerability, the server replies back with 65,000 bytes plus passed after the buffer, which is not normal by any means. Next, we have the shared library. This involves mainly C and C++ native libraries. This exponentially expands the application's overall attack surface just by introducing native functionality in the implementations. And as a result, it can actually create a whole bunch of different vulnerabilities from that at the low level. Next, we have input validation. This also arises due to user error and developer error. So it is whenever a function actually fails to properly sanitize and validate data being inputted. This can lead to a multitude of different critical vulnerabilities. And next, I'll be handing it over to Hahna to go over fuzzing.
So vulnerability analysis can be a very time-consuming and laborious process, and it can be manually intensive. Luckily, there's a way that we can do this at scale in an automated fashion using fuzzing. What we're doing is that we're sending crafted inputs to a target and monitoring it for crashes. And the application may crash for different reasons, such as making incorrect assumptions about the user supplied data, or not having the necessary functionality to handle that data properly. There's different types of fuzzers and fuzzing techniques that are out there. What we'll touch upon is running a mutational fuzzer, such as AFL or AFL++. A mutational fuzzer essentially takes an initial file as, it's called a seed, and when it sends it to the target, it's going to modify or mutate that data to see how the target then responds to that mutated form. Here's an example of running AFL and AFL++ against an Android application. And within 19 seconds, we had a unique crash. And within 25 seconds, we also had 3 total crashes that all demonstrated the same type of crash. So again, check out the ASRP for other types of fuzzing techniques and fuzzers that we recommend, but usually using a mutational fuzzer like AFL or AFL++ is a great starting point. So now, once you've found your vulnerabilities, you need to bypass all the Android security features that have been implemented, and so Jacob's going to discuss how to do that.
So upon actually pinpointing a vulnerability that we can potentially exploit, it's time to bypass some exploit mitigations. So to start off, we have the execute never / no execute. Execute never is specific to the ARM architecture, whereas no execute is specific to the x86 Intel architecture. So the NX bit is actually in charge of marking the stack as non-executable within your program upon compilation. And as a result, whenever the NX bit is implemented, this means that the attacker can no longer inject shellcode directly onto the stack, expecting it to be executed. So as a result, when the NX bit is enabled, the attacker will then have to rely on a method known as wrapping, or return-oriented programming. Essentially, this is whenever the attacker enumerates various different gadgets within the binary itself and can then manipulate the call stack as well as return addresses in order to bypass the NX bit to gain the functionality needed to carry out their mission. Next, we have ASLR, or Address Space Layout Randomization. This essentially randomizes the addresses within the virtualized address space for all of the executed programs that are within the virtual address space. It should be noted that ASLR is actually an operating system function, and it is not a binary function. However, it can be bypassed with an information leak. Pre-existing to that, before ASLR was actually implemented, exploit developers were actually able to hard code various addresses and other important information within their exploit scripts, and because they didn't have to deal about ASLR. However, since ASLR is now randomizing addresses every time the binary is executed, we have to rely on a pre-existing vulnerability that leverages a leak, memory leak, so that way we can obtain the base address, get an offset of that so we can recognize where we are within the code. Next, we have anti-debugging mechanisms. So this is just a generalized attempt to make dynamic analysis more difficult. You can actually see by the two pictures that we have anti-Frida and anti-GNU debugger. Essentially, these mechanisms will persuade the researcher from not being able to utilize these tools because the application might invoke some function calls that will look for these various types of debugging tools in an attempt to stop us from being able to perform debugging. And if they are found, then it can result in a premature termination of the application. However, we can utilize dynamic instrumentation to bypass these various anti-debugging functions, and we can also utilize a couple tools to patch our binary. Next, we have anti-reversing mechanisms. This is just an attempt to make reverse engineering much more difficult for the attacker. This is employed while within the source code itself for the original implementation. This can be employed in a couple different ways, such as encoding techniques, such as polymorphism, as well as encryption. So we can actually leverage a couple tools within our Android security research tool belt and utilize various deobfuscation techniques to get around that. Next, we have anti-VM mechanisms. This prevents the usage of virtualization technology while we're actively debugging and looking at our target during dynamic analysis. Ultimately, this can be bypassed by modifying a variety of checks as well as functions that are handling the anti-VM checks. And we can also do that utilizing Frida for dynamic instrumentation. Next, we have root detection. So root detection actually identifies if a device has been rooted or not. So rooting is similar to jailbreaking on an iOS platform. And why would somebody want to root their device? Well, this is simply because this allows them to be able to unlock all of the restrictions on the device, pretty much allowing them to do whatever they want with the device. So a couple ways that we can get around this is, once again, we can utilize dynamic instrumentation via Frida, or we can hook into various different functions as well as patching the APK itself.
Cool. So once you have bypassed these exploit mitigations and security protections, you can now proceed to attempt exploiting the vulnerability that you found. There's different types of exploitation effects that you can perform. We'll just touch upon a few of these, but again, we go into greater detail in the ASRP. So one of the common attacks that are observed are pin lock defeats. Again, in order to access your device or an application, it might ask you to enter in a 4-digit PIN, for example. Well, we can actually bypass that check by either hooking into the function and changing the implementation of that check pin function. We can also perform brute forcing depending upon the length of the pin, or we can actually directly invoke activities within the application that don't have the pin protection in place, right? It's most common where there's a lot of activities that aren't actually protected by the 4-digit PIN, so I can quickly invoke it and get access to your photos, videos, or any other sensitive data. We can also perform local privilege escalation. So as a standard user, you usually have a limited subset of permissions in order to read, write, or execute data on that device. With local privilege escalation, you can elevate your privileges to root, which has the highest administrative access, where essentially you own the system and you can read, write, and execute whatever you want. We also have remote code execution. So instead of having direct local physical access to the device or application, based on the vulnerability, I could potentially install an implant or execute a reverse shell, which will communicate to a different device. And now I can access my target remotely and execute arbitrary commands. In addition, there's an emerging trend of zero-click exploitation, where essentially an exploit can execute without the need for user interaction. What that means is that essentially a user is unaware that their device or application is being exploited. It's usually running very stealthily in the background without the user's awareness for however long that attacker wants. So again, these are different types of, I would say, cyber effects that you can demonstrate in order to showcase the severity of the vulnerability that you've discovered. Now, we have covered a lot in this talk, but we've only scratched the surface, right? If you want to learn more, definitely check out the ASRP, the Android Security Research Playbook. Again, it's a getting started guide for conducting Android security research, but also if you are a seasoned, experienced Android security researcher, I'm very confident there's going to be additional tips, tools, and techniques that you're going to learn in this. Again, you can access it on GitHub via this QR code. We also have a dedicated website for ease of navigation, and you can access them at these URLs, again, if you don't trust the QR codes. So with that, we're doing great on time. Any questions from the audience? This is a packed room, by the way. This is amazing. This is awesome.
This is awesome.
Go ahead.
You guys are obviously building out amazing exploits for Android phones. Are you seeing that more in scope on your pen testing or red teaming engagements? You're utilizing those exploits for those purposes?
So we're seeing, I would say, increasing requirements in order for the customer to understand what is the severity of these vulnerabilities. And even if we do report a vulnerability, they want proof, right? And so by developing these proof of concepts, we can showcase what is the risk if they do not patch or resolve that issue. And of course, for certain vulnerabilities and certain targets, we do go through a responsible disclosure process as well. Yep. Go ahead.
So you mentioned like OSINT and historical research at the beginning, and I understand that when it comes to like clients or whatever, but like I know, for example, like if I'm just a hobbyist, I'm like, oh, this place has a bug bounty, let me decompile it out and look at it. I don't necessarily need to do research there. So can you speak more on the OSINT and historical research maybe as a client perspective? That's what I was picking up on.
Yeah, absolutely. I'm going to pass this to Jacob because I'm going to say it's not client specific, but actually a critical initial first step that you should do for any target that you're looking at.
Interesting.
Yep, good.
Yeah, so overall, whenever you're introducing and actively utilizing your hacking methodology, no matter what your target actually is, the first thing that you want to start off with is reconnaissance. This allows you to understand the overall implementations and allows you, like if you get stuck anywhere during your security research, it allows you to have a soft spot that you can land back on if you need to pivot if you get stuck anywhere. So yeah, there's a variety of reasons why you would want to definitely perform reconnaissance and learn more about the target prior to actually getting into the nitty-gritty and beginning to perform static and dynamic analysis and look for exploits.
So I'll elaborate on that. So for example, if you want to understand what's the history of the app, right? Has it been around for 10 years or has it been around like last year? With that, and looking at like the release notes, the change logs, yeah, you can see how has this application evolved over time. And in addition, how many CVEs have been reported for this target over the years? Am I seeing more buffer overflows, use after freeze? Are they implementing newer security mechanisms that I need to take into consideration? So there's a lot of rich information in that history.
I see. So in that case, we're still talking about the target application itself.
Correct.
Not necessarily
Correct.
by or whatever, but.
Correct, you have the application itself.
Yep.
Because when I hear OSINT, I usually think talking about looking at people or companies or whatever, but this is about the application.
Yeah, so in this case, the target is the application, not the person or company. Yeah.
Thank you.
Yep, so
Yep.
you can actually utilize OSINT for a multitude of different capabilities and purposes. Yep.
Good.
Hey, out of curiosity, is there a playbook for doing reconnaissance and debugging the Android on a kernel level or on an operating system level?
That is our next sequel.
Yes.
So currently, we are focused primarily at Android userland, but we do want to release a second version that dives deeper going into the Android kernel. But also, for example, if you're reverse engineering the shared libraries, if they're making any particular kernel calls, right, that can lead you down that path as well. But more to come as far as playbooks. Yeah. Go ahead, and then I got you in the back. Go ahead.
When you guys are doing vulnerability research, which seems like the focus of your team, do you guys also kind of dabble in malware research and understanding what threat actors are doing with the vulnerabilities that you're coming across?
Yeah, so we actually take a hybrid approach, and that's one of the things that's great about our cybersecurity practice area is that we will collaborate with red teamers and also our malware analysts as well. So we're sharing our knowledge, and if we encounter any blocker, we'll reach out to the team saying, hey, this is what I'm seeing, and having that hybrid approach allows us to essentially complete our analysis much more quickly and more thoroughly.
Cool, thank you.
Yep, in the back.
Maybe this is a dumb question. Are we talking about attacking the application or the operating system or both? Because doesn't the operating system sort of limit the ability of the application to an attacker?
Great question. So we're focused on exploiting any vulnerabilities in the application. However, as Jacob mentioned during the exploit mitigation and security protection section, there are OS protections that are implemented that restrict what an application can do, right? So the execute never, for example, or the no execute, ASLR, et cetera, any of those OS security mechanisms we also have to take into account in order to successfully exploit our Android application.
So do you often run into applications that are already bypassing those on purpose and have more functions like bad coding practices and stuff like that?
I wouldn't say that they're actively trying to defeat them, but more of they're either not taking them into account or they're adding their own on top of it to make it even harder. Yeah. We'll go here and then here.
If you only have access to a production build of an application, what are your best practices for deobfuscating it?
Oh, great question. So, I mean, it's going to vary based on what obfuscation techniques that they're utilizing. But one, I would say an initial first step is like within JODX. They have different types of obfuscation techniques that you can implement. And then depending upon the category of obfuscation, let's say, for example, white noise or anything, or even, we'll say, function or variable renaming, there's additional techniques that we can take. You want to elaborate on that at all?
Yes, so by utilizing JODX, we can actually load in that target APK, and there's an automated method similar to Ghidra's approach to pre-analysis, and we can actually leverage that to deobfuscate that binary. So yeah, definitely something to look into.
Yeah, but in addition, I would say based on the complexity of the obfuscation, more likely than not, you have to develop a custom solution to do the deobfuscation. Yeah.
Makes sense.
Yeah, and then we had this guy. Yeah.
Have you seen anything in the
Great question. Personally, I have not. Perhaps on our red team, they may encounter more of that. But I would say that as companies are embracing more of like BYOD or bring your own device, they are recognizing the need to have better detection response policies for mobile devices. Also, if they're issuing work phones, for example, having some sort of mobile device management software is also useful as well. So, but again, for our research in our focus area, not necessarily, but great question. Cool, got you. And then I think you might have a question. Go ahead.
What's your opinion on APK tool? Does it work when you get it?
It works every time for us. But again, it's going to vary depending upon the target, right? As well as just the I would say the age of the APK that you're analyzing. But again, like it's not necessarily perfect, but it definitely gets the job done, at least 80%. So, anyone had a question over here? I think maybe. No. All right. Oh, go ahead. Sorry. Yeah, the light's blinding. Sorry. Go ahead.
I just wanted to know if any of the techniques that you're using are impacted by Android forks, like Graphene OS or Calyx or some of them. Does that change anything in what you're doing, or is it?
So I would say with the ASRP that we've released has been, I would say, the most effective method across the fragmented Android ecosystem. However, depending if they are using a different flavor of the Android OS, then we need to take more time to understand what those variations are and how they're reflected in the, say, disassembly that we're reverse engineering, right? So I would say it's not necessarily a one size fits all, but it definitely gets you like 80% of the way there, and then you just have to understand the nuances of your target to cover that remaining difference.
We're right at time.
Excellent.
Hahna, Jacob, thank you guys very much.
Thank you.
Thank you.
Awesome.